Here's another problem. We're moving to counting problems. And number 10 here should be a fairly straightforward one. In how many ways can I line up 7 members of an 18-person class in order? So the lineup, and especially the in order, is a big clue. We're going to be counting with order. And when you line people up, you can't put the same person in 2 different slots, so it's without replacement. And so that's NPR. And even if you don't recall the notation, we can really take it back to the fundamental counting principle. There's 18 choices for the first person in line, 17 for the second, 16 for the third, and then that's just going to be 7 numbers because you make 7 different choices. That goes down to 18 minus 7 plus 1. And if you just list out the numbers, fill in the dot dot dots, you can convince yourself that really is 7 different numbers. Now, to get the actual number and get an idea of the magnitude of that, you can go ahead and put it into the calculators, 18, then go to math, probability, and do NPR, and then 7 and enter, and that'll give you this number. A lot of people want to write this out with factorials, with ratios of factorials, and I just don't think that's particularly useful in most cases. It's a way to discover a few things about NPR and NCR, but I think it's misleading to focus on that. So I would just think about it, if you insist on doing it by hand, really calculate the product of all these numbers with the 15, the 14, and 13 put in, or if you're going to do the calculator, just go ahead and use that. Okay. And it's pretty big, 160 million. That's a lot of ways it can happen. Next one, okay, out of a class of 13, we select a group of 4 lucky students to get fudge brownies. In how many different ways can we make this choice? Give it an exact answer. So here, there's no indication that there's anything special about one brownie versus another, or that one student's going to be more lucky to be picked first or second or third or something like that. So that's going to be without order. Order doesn't matter. But you actually really are taking 4 students, not one student and then that student get selected twice or something like that. So it's going to be without replacement. And so here it's going to be NCR, 13C4. Again, you can write that in terms of ratios of factorials, but I don't recommend it, almost always. Really, that's just the fundamental counting principle. We can actually count them with order to use the structure, 13 times 12 times 11 times 10, and then we correct for that, because that's overcounting, because we really don't care about order. Divide by 4 factorial. And again, to get the number, it's easier just to put in 13, go to NCR, 4, and you get 715. And we'll come back to these numbers very soon in another role, in their role as the binomial coefficients. But these are supposed to be, I hope, fairly straightforward ones. Okay, this one, again, a card problem, but not nearly as hard as the poker hand problems that we often do in class. 6 cards deal, pay attention to that, from a 52 card deck. What's the probability of getting all hearts? So this is rather similar, it's very close to the probability calculation of getting a flush. But here I'm being a little more specific to make it a little more easy. Just that they're all hearts, okay? And we want I wanted a very accurate number here, just because it's, I want something to a lot of decimal places because it's actually a small probability, okay? So my suggestion would be to do this without order, okay? So count without order, and that means the denominator, all possible 6-card hands are, you've got a pool of 52 cards, and you're taking 6 out, and we're not paying attention to order, so that's absolutely a standard counting problem, just like the previous ones, 52C6. Now, what about the numerator? What are all the ways I could specifically pull 6 hearts out? Well, it's the same thing, it's just that you only can use the hearts. So it's as if you purposely just took the hearts out of the deck and figured out how many ways to deal yourself 6 hearts. So that's a pretty straightforward way, pretty straightforward way to do it for this kind of problem. Those both come out of the calculator pretty easily, and you get a pretty small probability. Let me see. This, you might want to double check this. I don't want to delay the video, but that number looks a little bit small to me. I hope I didn't accidentally do 52C5. Okay. I can double check it later. I'll put a comment on it if that really isn't the right number. But it's the same idea. It's the right idea. 13C6 over 52C6. Pretty unlikely to get that. Okay. Here's one more. It's a little bit more challenging. It's similar to a problem I have in the handouts, but we didn't really focus on it. From a class of 20 students, I want to choose 4 students to go to the library, 7 to go to the dining hall, 6 to go to the music building, and 3 to go up onto the roof and cause trouble. I'm not sure why I wanted to do that. Okay, and how many different ways can I do this? So it should look somewhat like an NCR problem. You got a pool. It's without replacement because students can't get, like, the same student can't get chosen twice to go to the library, for example. It's without order because one of the 4 students to go to the library, I don't care. Except I do care whether a student goes to the library, goes to the dining hall, goes to the music building, or goes up on the roof. Those are different. Okay. And so it's a little bit like NCR, but really what it's exactly like is distinguishable permutations. Okay. We've got a bunch of objects, and some distinctions don't matter, whether it's the first student or the second student or the third student picked to the library, or whether it's the first through seventh to go to the dining hall. But I do care whether the student goes to the library or goes to the dining hall. That's a meaningful difference. So one way to think about it, in any kind of problem like this, where you have multiple divisions that a group can be put into, and they're all kind of sorted into a bunch of divisions, and you don't care about the order within the divisions, is think about lining them all up, so that's 20 factorial ways, okay, and then correct for the, and so that could be like, okay, the first 4 will go to the library, the next 7 will go to the dining hall, the next 6 to the music building, the next 3 go up on the roof. But I'm going to correct for the fact that I don't care about all the different ways, these 4 students, just trying to cut and paste here, I don't care about how they can reshuffle themselves, so I'm going to divide by 4 factorial. I don't care about all the ways the next 7 can reshuffle themselves, divide by 7 factorial. I don't care about all the ways these guys can reshuffle themselves, etc. Or another way to make it exactly like our standard kind of distinguishable permutation problems, which are like anagrams, just line up the 20 students and have a bunch of cards marked with 4 L's, 7 D's, 6 M's, and 3 R's, and then just shuffle them, make some anagram, and then hand them out to the students who are lined up. Okay, so that's exactly one of our distinguishable permutation problems. And again, it's the same reasoning. How many ways could I reshuffle those cards if I could tell the difference between all of them, like even between 2 L's, 2 D's, or 2 M's, 2 R's, and then correct for the fact that I cannot tell the difference between the L's. I cannot tell the difference between the D's, the M's, or the R's. So these tend to be a little bit more confusing for people, but they're really good to recognize that this is again one of our standard counting problems, but one of the slightly more complicated ones. Okay, again, a really big number. Even though I divided out by some small factorials, that 20 factorial was really big. So here's one that I sometimes ask, excuse me, as a challenge problem on a test. Although I guess once I make this video, I won't do it anymore. But something that does focus more on factorials and powers and things like that. So which is larger, 100 factorial to the 101 or 101 factorial to the 100? And here the one good way to do things is we know that factorials like to be divided by each other. And so this is one of the few cases where I've actually written something out explicitly as a ratio of factorials, because this is the right way to do that for the distinguishable permutations cases. And we know good things happen when we divide factorials. And so these aren't just straight up factorials, but they have factorials in them. So a good hint is whenever you have factorial expressions you want to compare to each other, you should divide. And so I'm going to divide one by the other. It doesn't really matter which one, just keep track. I'm going to divide the 100 factorial to the 101 over the 101 factorial to the 100. And then I'm going to use the fact that I know some things about how factorials and powers work. I want to relate this guy to something involving a 100th power, because that's what's the power down here. Oh, I can just split off one power. That's 100 factorial to 100 times one more factor of 100 factorial. Okay, just using rules of exponents. Here, I want to relate this 101 factorial to a 100 factorial. Oh, wait a minute. 101 factorial is related to 100 factorial. It's 101 times 100 factorial. I can use another rule of exponents in the bottom here. I got a product to a power. That's the first thing to the power times the second thing to the power. And now I've got a cancellation. That guy cancels against that guy. And what do I get? 100 factorial over 101 to the 100th. Well, those are very different looking kinds of objects. So what I just did is started to write them down and say, okay, that's 100 times 99 times 98 all the way down to 1. 100 things multiplied together. But on the bottom, it's 100 things multiplied together, but they're all just either slightly bigger or a lot bigger. And so 100 over 101, that's less than 1. 99 over 101, that's less than 1. 98 over 101, and they match exactly. There's the same number of things top and bottom. So this is substantially less than 1, and therefore the denominator is the one that's bigger. Okay. So a good use of sort of the basic rules of how factorials work. Really, all we really used about factorials, well, up till the very last, I guess. But the main thing we used is how you relate one factorial to the previous one. And this is how you relate one power, the 101st power of something, to the previous one. Another good way to approach these, I didn't write this down, excuse me, but if you're mystified by one of these problems where the numbers are staggeringly big and there's no way you could possibly calculate them, what I'll just do right now is what you could think about is what's bigger, like 4 factorial to the 5th. Now that's still a pretty big number, but it's not quite so scary. Versus, let's say, 5 factorial to the 4th. Okay, you could even go down to like 2s and 3s, I suppose, and you'd still get the right idea. And if you could analyze these and they're a little bit more friendly, and then you could kind of get an idea of, oh, okay, there's some cancellations. I can see the correspondence. So that's always a good strategy when you have challenging problems with big numbers. Try out the corresponding problem with small numbers, and then see if you think you can see the pattern from there.